Today we're going to be looking at the training data generation subproject. This is an application which calls my fluid simulation framework to generate many simulations which are going to be used to train the neural network. So we use the pre-built fluid simulation framework as an input to this. This is a shared library which we can see that's included in the project here. I'll give a quick rundown of the application in the source code. Essentially we have two classes, the job generator, the job dispatcher. The job generator creates variations of the simulation jobs, returns a queue of jobs, and a struct which defines global configuration of each job. We then have the dispatcher which actually runs the job on the GPU by calling my fluid simulation framework. It logs the information for each job and caches it to disk. Additionally, it also generates keyframes which we can view to view the simulation to check visually for the quality of the output. So the job generator, like I say, essentially defines these types, which is the job payload, which defines a single job. These are all free parameters. These can vary per job. For example, the types of collision, the boundary conditions used, the sourcing terms, the advection schemes, the projection schemes. This returns essentially a pair of a job vector or a queue, and also this configuration struct, which is the global state of the job parameters. For example, things that are fixed for all the jobs in the generator. So things like the resolution of the grid scale, if the colliders are moving or static, the name of the generator. So this is done here. First of all, the first operation is to index the meshes. This is the 3D models that are going to be used to collide with the fluid simulation. Not every simulation will have a collision. That's determined by this parameter here, if mesh collider is used or not. And we use a random boolean here based on a distribution, probability distribution. All the other parameters are also defined by these ranges, which are predefined but can be edited publicly. For example, like the translation of the source, the velocity of the source, and these are passed into these random functions here, which are wrappers around the standard library random function. So for example, we have some deterministic random functions which I've written. These are based on the job ID seed, and then we also have these non-deterministic ones which just use the system clock as the seed value. So this allows us to get, pseudo-random numbers to define the parameter ranges, and hopefully by generating enough jobs with enough frames we'll generate a good variation of the parameter space which can train the neural network so it can generalize to novel situations. The dispatcher class then takes this job output returned here and we pass it in as a reference. We also pass in a bunch of directories, the cache directory, the script directory, and a few parameters. This one parameter here is the residual tolerance. So because we are using the pressure solver in the training data, because we want the simulations to be somewhat incompressible, we define a tolerance. This tolerance actually won't kill the simulation if the pressure residual falls above this, but it will warn us in the log file. Then we call dispatch, which we specify the job output, the number of frames to generate, and the nth frame. For example, we don't need to generate a full sequence of caches for each job. We can only generate n frames if we want to save disk space. The dispatcher then takes the jobs. It's a singleton class, so we just fetch the reference to it. We pass in the job output, as we've seen here, and then we essentially go through the queue, get in each job. We generate a new fluid object in Fluid Solver from my fluid simulation framework. We specify all the parameters from the job payload specified here, and then we essentially call the fluid solver, which happens here. This generates, the simulation for the number of frames specified. We also write the cache directory, and we also write this job file, a .job file, which specifies all the parameters used for the job so that we can view them later on. Finally, we call the Fluid Viewer application, which is a separate application I should have covered, which we generate what I call QA frames, which are quality assurance keyframes, and these render the fluid simulation from an orthographic view with the job info displayed, so we can debug visually each job to check for any errors, and we can call jobs that we think are not going to be useful to the neural network. So if we do a quick demonstration of this, this is the main function where everything's called. We have some basic arg parsing, and we can specify what args to pass. So we call the application, we specify the cache root directory, we specify the mesh root directory of the meshes we want to use for collisions. The grid resolution is 64 cube currently, the grid size is 1 cubed, it's a unit grid in world space. For this example, we'll only generate 2 separate jobs. Each job is going to be 20 frames long, and we're going to cache every nth frame where n equals 1, so we're caching every frame essentially. Finally, we pass a script directory root, and if we execute this, we can see that we have 2 jobs generated. The first job here, we list the parameters in stood out, so we can see all these different permutations that have been created. So this job has McCormick advection, it has correction strength of 0.5. Then we saw the fluid viewer just flash up, and that essentially is generating those keyframes which I talked about, which we can see on disk afterwards. Job 2 is running now, or job 1, should I say, zero-based indexing, and yeah, and the same thing. And now it's done. So we see each job took around 13 seconds. If we look in the cache directory output, we can see 2 jobs. We have the binary cache files. We have a header, which is just a small file which specifies the grid dimensions, the grid size, and the delta x size. And we also have this job file, which I mentioned, which lists all the parameters, which include the job name, the job ID, stuff like the mesh collider name, the mesh collision position in world space, the advection scheme, essentially most of the parameters that we saw in the job payload. Next, we have the QA folder, which is created, and this has a sequence of images which are called the fluid viewer, and we can see that we have the job file displayed here, so we can visually debug. For example, we see this simulation isn't very useful because the actual density source isn't colliding with the collision source. So we could just call this collision, and we could just call this simulation because the collision is not very useful. Next, we'll look at this job's QA frames. Again, this job doesn't seem too useful. We can see that there's no grid collisions, so the smoke is just moving out of the grid, and the collider actually isn't being hit by the job. So it's a bit of a guessing game to get good simulations, but essentially running hundreds of simulations on multiple GPUs, both on my own machine, my spare machine, and possibly in the cloud, will allow me to generate lots of simulations. The caches are not huge. They are in a binary format, but they don't use compression. But they should give us enough variation that we can then pass these into PyTorch, into the neural network, to be able to train the neural network to predict the pressure. Now, the visualization of output here is just density, but we're also going to output QA frames for the divergence, which is the right-hand side of the Poisson equation, and also the pressure, which we can compare with the neural network output.